Welcome to our technical video for our project, Visualizing Transport Equality in Singapore, presented by the Subway Suffers Bike and team, that's Parody, Dong and Qianlong. You have seen how our app works in action in our front-end team's video. That's cool, right? So how did we build it? We used R and Python for the project. R handled all ETL tasks, which are extracting, transforming, and loading data. Python was used to query the OneMap API. For our destination points, we manually collected all latitude and longitude for all public hospitals and polyclinics in Singapore from Google Maps. We divided Singapore into 53 planning areas and 323 subzones. For example, Ang Mo Kio includes subzones like Ang Mo Kio Town Centre, Cheongsam, Chong Boon, and so on. Since our data source was in TypeScript format, we used regex in R to extract each subzone's representative latitude and longitude. This is what our final starting point dataset looks like. With both origin and destination coordinates ready, we used the Harvard sign formula to calculate heuristic straight line distances. This helped us identify the 5 closest public health facilities for each subzone.
We then queried from the OneMap API by setting the route type to PT, public transport, and selected mode as transit. From each API response, we extracted these key information: total travel time, walk distance, number of transfers, and transit time. To analyze temporal variations, we performed queries across various time settings shown here. Specifically, we selected Wednesday, March 19 for weekdays, Saturday, March 22nd for weekends, and National Day on August 9 for a public holiday. We also considered a range of times, from morning to evening, to capture both peak and non-peak hours. For our accessibility scoring, we focus on total travel time, TT, total walking distance, TWD, and transfers, TRF. We excluded walk time as it is highly correlated with walking distance, and transit time, which is closely tied to the number of transfers, as can be seen in our plots here. To ensure that all our factors are on the same scale and all values lie between 0 and 1, we applied min-max normalization. This way, no single factor would dominate the score due to its scale. Our accessibility score is calculated using the formula shown here, with each factor being subtracted from 1. This inversion ensures that lower values, which indicate better accessibility, are rewarded, while higher values are penalized. We introduce an exponential decay factor, e to the power of negative lambda d, where lambda is the decay parameters set to 0.15 and d represents our heuristic distance. This adjustment prevents routes with longer travel distances from being penalized disproportionately, as the exponential function tapers off gradually, unlike linear or quadratic penalties, which continue to decrease steeply with distance. Additionally, the exponential form ensures that accessibility scores remain positive and never fall to 0 or negative values. The exponential decay reflects observed travel behavior, where individuals are much more sensitive to small increases in distances when the destination is nearby, but less so when the destination is already far. And finally, the technical challenges we faced. The biggest challenge was slow query times, even after segmenting planning areas and running it in batches. Also, to enhance user experience, we could consider introducing real-time querying. We also see the potential to extend coverage beyond just healthcare facilities to other essential services like schools and commercial places, broadening the impact and usefulness of our app. That would be it for our technical video. Thank you.